Hey, so we should be Monday the 23rd today. Again, you can, of course, work ahead or work behind or not work behind, but like if you fall behind a day or two, it's not a big deal, but want to get caught up. Should be basically the end of our simple harmonic motion section. So kind of doing some review problems today. We should have already done the mixed review, right? The mixed review that I put online and be able to do those problems. I'll work through those problems here in a minute. I'm thinking probably then Tuesday we'll do a little quiz. If as we're going through stuff, everybody's not feeling comfortable, want to let me know and we can maybe shift things a little bit or work some extra problems or something like that. But anyway, we'll start with a little pendulum thing. I thought we had already done this earlier this year when we were doing energy, but Tom Jack was complaining that we hadn't done this yet. So I might get hurt and I'll blame Tom Jack for that. So let's see if you can see me okay there. Yeah, I think you can see me okay. So I'm going to sit here. I've got my head against the back of the wall, right? And then I'm going to raise this up right to my chin. Can you see? I don't know if you can actually see me there. I can't see my computer screen all that well. So I'm going to shift it just a tiny bit. Make sure you can all the way see me there. And we'll hold it up to my chin, and then we'll let it go. And then let it come back up. And feels as it's coming back up like it's going to get you, right? But we know is that's in simple harmonic motion. Yeah, you really can't see a whole lot of that. You can just see it come up right there at the end. But it's swinging down through there. Yeah, you can kind of see it fly back and forth there. But anyway, as I carry the computer around so we can do this. Maximum potential energy to maximum kinetic energy kind of thing, right? So when you're holding it upright, it's maximum potential energy. You let it go, it falls down through to go to kinetic energy and back through and that kind of thing, right? So it's not going to come back up and hit you in the face because it's not going to get any more potential energy than it had there at the beginning. So going through our mixed review, chapter 12, vibrations and waves. Pendulum with a mass of 0.1 kilograms is released. As soon as I read that, I say, well, the mass of the pendulum doesn't really matter unless they're going to start asking me about potential energy or something like that. The string made a 7-degree angle with the vertical. Probably not going to matter. The bob of the pendulum returns to the lowest point every 0.1 second. So I've got to be careful there. It says it returns to the lowest point every 0.1 second. So it goes lowest point, and back, right? So that's kind of like on a wave, the nodes on a standing wave, right? That there's more than one node per wave. So there's more than one lowest point per oscillation. So it goes back and forth. So that means that the period is 0.2 seconds. And the frequency then is the inverse of the period. So that is going to be 5 per second, not 10 per second, but 5 per second, because that's lowest point. Now it's kind of low. So as I talk with my hands, you can't see me, right? B. Pendulum was replaced by one with a mass of 0.3 kilograms and set to a 15-degree angle. Do the following things increase, decrease, or stay the same? All right, so we're on 1B. The period is going to stay the same. The frequency is going to stay the same. The total energy will now be more because the bob is heavier and you made a bigger angle. So a bigger angle is going to be up higher. So the energy will be more and the speed of the lowest point will be more, right? So there's 1B. 2, a narrow flat steel rod is anchored with the lower end with a 0.5 kilogram ball welded to the top end. A force of 6 newtons is required to hold the ball 10 centimeters away from the central position. So it's up and you are pulling it this way and it wants to spring back that way, right? So we're dealing with like a spring pendulum sort of thing here, right? If this arrangement is modeled as an oscillating horizontal mass spring system vibrating with simple harmonic motion, find the force of the spring constant, K. So there we are to force equals negative Kx, I believe is going to be what's easiest to use for this. That's going all kinds of directions. Where the force is what they gave us, 6 newtons, right? So 6 newtons. And we're going to divide that by a distance of 10 centimeters, so 0.1 newtons. So our K is going to be 60 newtons per meter. Now, the negative here, right, that's telling us direction. So if the force is in the negative direction, then we'll also have this in the negative direction, and negative times a negative equals a positive. If the force is not in the negative direction, then the distance is, and you've got negative times a negative is a positive, right? So that's just showing us direction on there. So don't get too worked up about the negatives and all that kind of stuff there. That's this force is a restoring force. That's the name of that force. The period and the frequency of the oscillation. So it's a mass spring system. So period is going to be 2 pi times the square root of the mass of this thing. And the mass of this thing is 0.5 kilograms divided by the spring constant, which is 60 newtons per meter. So that's going to be 0.573 seconds, right? 2 times pi times the square root of 0.5 over 60 will give us 0.573 seconds for our period. The frequency would just be the inverse of that. So 1.74 per second, right? So it means you're going to get 1.74 oscillations per second. 3, find the acceleration due to gravity at a place where a simple pendulum that is 0.15 meters long completes 100 oscillations in 300 seconds. Could this place be the Earth? So we are comparing G to Earth's gravity, right? So again, period is 2 pi times the square root of L over G. They give us the period, right? They give us information for the period. So we'll go ahead and do let's go ahead and solve for gravity here. And so the length is 0.150 meters. And the period is the time it's going to take. So I'm going to do the 300 seconds over 100 oscillations. So that's going to be 3 seconds. So if we go to do those calculations, so if we do the calculation there, we get 300 oscillations in 100 seconds. So your period's 3. Divide that by 2 and divide that by pi. Remember, be careful how you put that into your calculator. Square that, do 0.15 divided by that value, and that's going to give us gravity, units over meters per second squared, of 0.657. So no, this could not be Earth. That seems like a really small value for gravity. I double-checked calculations there because I was like, what? But if we think about that, if I can find my pendulum here, that's 15 centimeters. So that's like this. And it's 300 seconds for 100 oscillations. So that means it's about like this, and it's taking 3 seconds to go back and forth, right? So this is going back way faster than once every 3 seconds, right? So the gravity here is significantly weaker than that on Earth, right? Okay, so number 4, on to the second page of the mixture view. Consider the first 2 cycles of a pendulum swinging from position A of 2 seconds, from position A with a period of 2 seconds, at which time is the bob found at positions A, B, and C in the first 2 cycles. So let's draw that up on the board here. Let's see. So I'm going the same direction you're going here. We've got A, we've got B, and we've got C. It starts at A, then it goes over to C, and then back to A. So at time 0 and at time 2 seconds, it's at A. So then at 1 second, it's here. So at 0.5 seconds and 1.5 seconds, it's at B, right? So at which times would the position be at A, B, and C? So since it's 2 seconds to go this way and back, 0 and 2 seconds here, 1 second here, and those there and there, right? Hopefully that makes sense, right? Because from 0 to 1 second here, and from 1 second to 2 seconds here. Right? B, at which times and locations is the gravitational potential energy at a maximum? A and C, not based on my drawing, but based on this drawing. Based on that drawing, A and C are at the same height. I can't draw, so C looks higher. But A and C would be maximum potential energy. B would be maximum kinetic energy, right? That's just like the pendulum I let swing at my face. You don't push that, by the way, or it will come back and hit you in the face. But it was maximum potential energy right by my chin, and then went to maximum kinetic, and then it stops, right? Let's see. At which times is the velocity at a maximum? That's at the bottom, B. Restoring force and the acceleration. Restoring force and the acceleration would be at a maximum at A and C, because that's where it's the most removed. Find the frequency is 5, right? On to number 5. The frequency of a pressure wave is 100 hertz. The wavelength is 3 meters. Find the speed of the wave propagation. So here we haven't done as many of these. But if we take the velocity of the wave That's going to equal the frequency times the wavelength, right? So they're asking for the velocity of the wave, right? The frequency is 100 hertz. So 100 per second times the wavelength is 3 meters. So that means at 100 times a second, a 3 meter wave passes you. So 300 meters per second, right? So 300 meters per second is how we would go about doing that. We haven't done as many of these. We hit these quite a bit in chemistry though, right? With our C equals lambda nu. In chemistry, they use a C for the speed, lambda for the wavelength, and a nu for the frequency. But in physics, they go ahead and use a velocity and a F for frequency. A pressure wave of 0.5 meter wavelength propagates through a 3 meter long coil with a speed of 2 meters per second. How long does it take for the wave to travel from one end of the coil to the other? Well, it's 3 meters. That's not even this. That's just a distance equals rate times time thing, right? So it's going at 2 meters per second. So 2.0 meters per second would be the velocity. The distance it needs to go is 3 meters. So if we do distance divided by velocity equals time, right? Or velocity times time equals distance. Right, so we do that, and we do 3 meters divided by 2 meters per second. That's going to give us a time of 1.5 seconds. Right, so 1.5 seconds. How many wavelengths fit in the coil? So how long does it take for the wave to travel from one end of the coil to the other? So that's going to be the 1.5 seconds. And then how many waves fit in the coil? Well, it's a half a meter wave, and it's 3 meters long, so that's going to be 6 waves, right? 6 waves would fit in the coil, right? And each wave, right, is an up and a down. So it'd be 6 of these in that coil. 1, 2, 3, 4, right? However many those are, right? So you'd have 6 waves with that being a wave, not that being a wave, right? So anyway, that's that. Hopefully, simple harmonic motion is pretty straightforward. Usually people don't have a whole lot of trouble with it. If we need to work more book problems or something like that, we can probably read that chapter review and stuff, and then let's figure out if we're ready for that test or not. I guess we're going to assume that we are. If we feel like we're not, if we feel like we need more practice, then you're going to have to let me know somehow, right? And a few of us do, then we'll add an extra day of practice problems or something.